Okay, so we'll do a little video lecture here because you will all be reaching this topic at a different time. So what we're going to talk about in this case is circular motion. And when we talk about the physics of circular motion, we have to think a little bit about acceleration and velocity. So first of all, acceleration is the change in velocity. So an object will accelerate if any one of three things happens. If an object slows down, then its velocity changed and it accelerated. If it speeds up, the velocity changed and it accelerated. And if it changes directions, the velocity has changed and so it has accelerated. So you can accelerate by speeding up, slowing down, or just changing the direction of an object's motion. And this is because velocity, of course, is a vector. Both the magnitude and the direction matter, so changing either one of those will cause an acceleration. Now, as we know from Newton, if an object accelerates, there must be an unbalanced force that's acting on it. If there's no unbalanced forces acting on an object, then it cannot accelerate. Objects in motion remain in motion in a straight line unless there's an outside force. So if an object slows down or speeds up or changes directions, we know there must be a force acting on it. So let's think about a race car. This race car is going around the track in a clockwise fashion. If we apply a force to the back of the car in this direction, as shown, that will cause the speed of the car to increase. The car will go faster. If, on the other hand, we apply the force in the opposite direction, right that way, if the car is already moving to the right and we apply a force this way, it'll actually slow it down. And lastly, if we apply a force to the car from the side, that won't speed it up, it won't slow it down, but it will cause it to change directions. And so if you want to change the direction of an object without changing its speed, you have to apply a force that is perpendicular to its velocity. So its velocity is to the right here. So forces that act perpendicular to the motion of an object cause the object to change its direction, not its speed. So if an object is moving this way, and you apply a force on it downwards in this direction, that'll change its direction. If this perpendicular force continues to act on the moving object, so you apply a perpendicular force here and that changes its direction. You apply it here and it changes its direction some more. If you keep applying a force perpendicular to the velocity, then you will get a very special kind of motion, and it's what we call circular motion. It will make the object move in a circle. So circular motion is what you get when an external force acts perpendicular to the velocity of an object and changes its direction, not its speed. So if I have, for example, a rock here and I'm swinging it in a circle around me, the rock, if you cut the string, would actually move in a straight line. That's the inertial path of the rock. But because the string is pulling on the rock, it's changing directions. And of course, when the rock is over here, the string is pulling this way. And when the rock is here, the string is pulling that way. So a central force or a centripetal force always acts perpendicular to the velocity, and it causes it to move in a circle. So forces that act continuously in a perpendicular direction on an object cause the object to move in a circle. And we have a special name for those forces. So a force that acts perpendicular at all times is called a central force or a centripetal force. This is from the Latin centri, which means center, and petal, which means seeking. So it's a center-seeking force. And they always act towards the center of the circle. So a centripetal force is not a new force. It's not like there's some forces and then there's a centripetal force. It's just the name we give to a regular force that causes an object to move in a circle. So friction can cause an object to move in a circle, like on a car. If a car is going around a circle here, it's the friction of the wheels that causes the car to move in a circle. Friction actually acts perpendicular to the direction of the car, and it keeps acting perpendicular, and it causes the car to move in a circle. It's easy to think about what would happen if there was ice on the road and there was no friction. This car would not have a perpendicular force on it if it was icy, and it would continue to go in a straight line. It would not move in a circle. So in the absence of a center-seeking force, objects would just move in a straight line. And so this car would actually fly off the road if the road was icy, and it wouldn't move in a circle. So that brings us to the question, how much force is needed? How much force do you need to make an object move in a circle depends on three things. First of all, it depends on the mass of an object, how heavy it is, because heavier objects have more inertia and they require bigger forces to make them change speed or direction. It depends on the radius of a circle. If it's a very big radius of a circle, that's pretty close to a straight line and you don't need a whole lot of force. But if you're trying to make it go in a very small radius, that's a very tight circle, you have to apply a very large force. So the force you need is going to be inversely dependent on the radius, because the bigger the radius, the smaller the force you're going to need. And lastly, it's going to be dependent on the velocity. The object that's moving very fast is going to require more force to make it change direction than an object which is moving slowly. So we put all these three things together and we can find that the centripetal force, the force required to make an object move in a circle, can be given by this relationship. The centripetal force is equal to the mass times the velocity squared divided by the radius. The centripetal force, of course, is in newtons, masses are in kilograms, velocity is in meters per second, and the radius of the circle is in meters. So take a second to pause the video and write that down in your toolbox. That's the second of the two equations we're going to use in this unit. And that, of course, is one of the two big ideas, the other being gravity. Okay, so let's just solve two example problems. You can pause these as you need to study them in more depth. How much tension or force does a string need to apply to a rock to keep it moving in a circle? So you've got a rock swinging around over your head maybe, and the radius of the circle is 1.2 meters, and the rock's moving at 5 meters per second. To figure out how much force you need to make an object move in a circle, I'm going to draw a little diagram. Here's my object moving in a circle. Here's my variable list. It's pretty easy to figure out what each variable is from the problem. And then you're simply going to evaluate our centripetal force expression and plug in the numbers, and you can figure out it takes 10.4 newtons of force to make the rock move in a circle. An interesting note, if you swung this around faster and faster, it would require a greater and greater force. And if the force that is required to make it move in a circle is greater than the tension of the string will break and the rock will move in a straight line from the point where the string breaks. Okay, let's do one more example. This one's a little more complicated. We're going to look at a brick. And think about a brick on the merry-go-round. So we have a 1.5 meter radius merry-go-round. A 2 kilogram brick is resting on the edge of the merry-go-round. And the merry-go-round is rotating 6 revolutions per minute. We call those RPMs. So in this case, you don't have the velocity of the brick directly. We're going to do a little calculation to find that. So the first question is, what is the velocity of the brick? And the second question is, what is the force that is needed to keep the brick on the merry-go-round and thus moving in a circle? So let's do the first one. What is the velocity of the brick? So in order to find the velocity of the brick, we have to use the 6 revolutions per minute. So it's going around 6 times in a minute. And we're going to have to use the radius. So the way it works is this. The velocity, of course, is the distance divided by the time. The distance that you go will be the circumference around the outside of the circle times 6, because it made 6 revolutions per minute. And we're going to divide it by the time. So the circumference of a circle is 2 pi r. We're going to multiply that by 6, and we're going to divide it by the time, which is 60 seconds. So plugging in the numbers of 1.5 meters is the radius, you can figure out that the velocity of this rock going in a circle of 1.5 meter radius, and it goes 6 times around in a minute, it's 0.9425 meters per second. So that's a good example calculation to hang on to. That's how you can use revolutions per minute to figure out the velocity of an object. You need the revolutions per minute and you need the radius of the object. Once you know the velocity, calculating the force that's needed is fairly straightforward. We simply evaluate the expression mv squared over r. We now know the velocity, it's 0.9424 meters per second. Put that in the expression and we calculate 1.18 newtons is the force that is required to make this rock move in a circle. Okay, before we leave, one last note. There is no centrifugal force. A centrifugal force is a mythical force. There is no force pushing you outwards. If your car hits ice, there's no force that pushes you out of the circle. It's simply your inertia, which tends to make you go in a straight line, and so you will not move in a circle. So there's really no such thing as a centrifugal force. It's really an inertia effect. Um, so what you really need is a centripetal force, which acts inwards, which keeps you moving in a circle.